again, folks, in MAT-114. Today we're going to be covering section 6-7, which is a slight modification. Today is President's Day. There's the calendar. February 15th. What I decided to do, even though you're not responsible, to even acknowledge this today, rather than do two sections, sections 6.6 and 6.7 on Wednesday, I'm going to record just 6.6 today and then do 6.7 on Wednesday, because I think just in looking at the material, it's going to end up being a rather long video. So I'm going to break it up into two videos. When you see this finally, there'll be the same link to the playlist for our class, but it'll be two separate videos, so just be mindful of that. Okay. If I don't think this pertains to anything in MAT-113, but since it's algebra, I might label it 090 as well as a supplement for the MAT-113 people. Okay. So anyhow, let me show you the packet that would be relevant. So this is quite a lot of pages, actually. Here is an overview that I had made. What is relevant to you folks in either MAT-113 or MAT-114 are just these three methods, all right, for graphing in two dimensions. That's what section 6.6 is about. It's graphing on a coordinate plane, X and Y. All right. I threw this in here. Usually I teach Algebra 2 or pre-calc, and they're required to have a calculator like this. Anyhow, graphing using your calculator is a skill, so even though I would definitely encourage a person to assimilate this information first and foremost, right, especially this method of the three, right, using your calculator, once you've mastered that skill, right, expedites getting to an answer of something more complicated. So if you happen to have a graphing calculator, all right, this is really all you would do. Press this button and this button. Anyhow, please don't do that when you're trying your MAT-114 homework, because you're here to, garner that skill. So you don't want to circumvent the learning process. All right. Anyhow, that is an overview. Here, all right, is a coordinate plane. We're going to fill in the labels here in a few moments. This is an input-output table that I had made. This is the most brute force method for graphing in two dimensions, but it works. And I always like to teach people this because it's empowering. Right? So even if you didn't have a calculator, even if you weren't familiar or comfortable with more complex methods, all right, this brute force method will get you out of trouble and pretty quick. All right. Anyhow, these numbers that I've used here, -1, -2, 0, 1, and 2, respectively, they will work for virtually anything. And you might wonder, well, why those numbers? Because they're small, all right, and they're easy to work with. 0 times anything is 0, right? 0 plus anything doesn't change the identity of what you're working with, all right? And it's a nice spread of negatives and positives. So if you had to graph something, again, that is unfamiliar, brute force, try these numbers. Try these 5. You can always do more than that, but that'll get you started. All right? This is the second method, which is using the X and Y intercepts described. All right? This is a table just to kind of get you going, all right, using that method. This is the description of the slope formula. I swiped this from the textbook. And this is a table for method 3, which is the slope-intercept form of the line equation. Right? This is the most efficient method, and even if you were using a graphing calculator, you would really need to be familiar with this of the three in order to utilize that. Right? And then we'll do a word problem. Okay? So if you're following along, definitely print this. Right? It's an overview, as I mentioned. So you see that you have alternative methods. All right, probably when you're doing your homework, it'll specify, hey, do it this way versus another way. In the long run, you'll have the option yourself to decide, and you'll do it, based upon, whatever is the most convenient for you. Anyhow, let's get to this. I'm gonna turn on my projector here, and hopefully, I didn't turn on my power. That's not good. I think I just killed my laptop. Oh, saved it. Thankfully, okay. That was a close call. My battery is not so great. Let me make it a bit darker. And if necessary, adjust the projector. Right. Here's Middlesex. Let me just pull up the page that is relevant. I'm going to be working with the coordinate plane. Let me show you something just for emphasis. What we had been doing previously was graphing in one dimension. Now, in theory, usually the way that you start when you're graphing in one dimension is that it's just a horizontal line. All right. I basically modified the graph that you're about to see to just include a horizontal line. Right? Here's 0 and here's infinity in the positive direction and the negative direction. This is from section 6.5. In theory, right, you could just turn the line vertically and it would still be exclusively graphing in one dimension. All right? Now, what that is practical for is when you're graphing inequalities, right? When there's a spectrum of solutions rather than one distinct or maybe two distinct answers. All right? When you're graphing in two dimensions, you need the two axes superimposed upon one another. So in a sense, the math universe, or math world, if you will, has expanded now. And that's why we're working with this. So there is, as often the case, a lot of labeling that is good to be familiar with. So I'm going to start with that. All right. And just to encourage some good etiquette. All right. This is firstly referred to as a Cartesian coordinate plane. Otherwise, you can just call it a plane or a 2D plane, graphing plane. A 2D graph because it has this axis and this axis simultaneously. Right? In theory, if you were to go to calculus, and believe me, you can handle that, whether you feel comfortable or not. You really can, though. All right. There's just a third dimension. All right. And what it would be is an axis, the z-axis, all right, which is depth, right? So it would be coming out toward you, It's a little bit harder to graph those by hand, which is part of the reason why mathematical software has been created. It makes visualizing three-dimensional graphs much easier when you use gradient sort of shading, Anyhow, we're in 2D world for right now, flat world. All right. And the standard labeling for this axis and the vertical axis is the x-axis and the y-axis. Incidentally, this is called the Cartesian coordinate plane because it's named after French philosopher René Descartes, right, who lived in the early 1600s. Right? He's famous for that expression, I think, therefore I am. And also this, among other things, right? Math world, the flat version of math world. Anyhow, 0 is here, and it has a name which is referred to as the origin. Origin, whatever have you. Looks like tomato, tomato. All right. And the alternative labeling would be to refer to the x value and the y value at any particular point. Right? So it's not just one thing, it's two things always simultaneously. An x value first and then a y value second, and it does rigidly have to be in that order, all right? And if we're talking about the origin specifically, all right, where the axes cross here, that point, it would be 0, 0. It is neither right nor left, nor up nor down. It's dead center. All right. These particular regions, which is created by the axes here and here, all right, are labeled with Roman numerals. All right. Now, bear in mind again, this comes from the 1600s originally. It's medieval math. Right. Well, it's past the Middle Ages. This is the early modernity. Right. But they were still using Roman numerals a lot, at least for purposes of sort of tradition. If you went to school back in the Middle Ages or in the Renaissance or a little bit thereafter, really up until the 20th century, you were guaranteed to learn Latin and Greek. It was always a requirement, at least in Western in Europe. Anyhow, this region is referred to as quadrant, because it's one of 4, quad, right? 1, Roman numeral 1, right? And it is read counterclockwise. So if this is quadrant 1, this would be intuitively quadrant 2. Quadrant 3, it's like Rocky movies, right? And then quadrant 4, IV. Right? Now you might say, well, aside from the labeling, what practicality does that have? Right? When we get into the conversation of slope, which is a number really that decides the pitch or the incline of a line, it is good to use these as sort of a vague reference. Right? So for right now, just understand that this is quadrant 1, 2, 3, and 4, respectively. Insofar as the value of the x's, which would be, again, incremented along the the horizontal axis, 1, 2, 3, 4, 5, and you could label them if you want, but it gets a little messy if you do that. The value of the x and the y, ordered pair, which is what they refer to as, would be as such, both positive. Right, so if you have a positive number, whatever it is, the x value, and for your y value, it is an implication that you're working in this particular region here, okay? If you have a negative x value and a positive y value, you're definitely in quadrant 2. Right? If the numbers are both negative, then you're in quadrant 3. Right? If the numbers are in, one of each again, a positive x but a negative y, then you're in quadrant 4. Okay? Anyhow, officially these are referred to as ordered pairs. Very often, and I do this myself, I just refer to them as coordinates. Right? The x coordinate and the y coordinate. Anyhow, when you are graphing, you must resist the temptation. Let's say, for example, you had to graph the coordinates 2, 3. Right? You must resist the temptation to actually make a mark until after you have moved the y portion of the ordered pair. Right? So in other words, don't do this. Right? If you had to put a dot where, and that all it is, plotting is dotting. If you had to put a dot in place of 2, 3, you would always start out at the origin and you would count over 2 places. But don't put a dot here yet. This is a mistake a new person usually makes. So you go, okay, from the origin 1, 2, resist the temptation to make a mark, and then move the next amount, which would be the y amount, up 3, 1, 2, 3. And you will put a dot here. Right? That is that ordered pair. Right? You do the x portion of it always first, and the y portion of it always second. Right? And you don't make a dot until after you've moved y. Okay? Now you might wonder, well, how did you decide that one way is up or down or vice versa? Right? Let me put that over here because I'm running out of space. The way that it works is that for x's, you're either going to move left or right. In which case, right is designated by positive and left is designated by negative. All right. For y values, you're either going to move up or down. And as far as signs are concerned, up is indicated by a positive symbol, or sometimes it's just not bothered to be written, and down is a negative symbol. Right? Left negative, down negative. Right positive, up positive. Okay? I think that is pretty much everything you need to know about the actual graph. Let's move on to methods now. You may find, and I would encourage this, when you're following along, if you are, right, print this several times so you don't have to draw it, all right? It can be a bit of a nuisance. Obviously, you can get a ruler, a pencil, and some graph paper, all right? But I made this for you guys who are in my class at least to print, so that it would spare you from having to reinvent the wheel every single time you need to graph one of these things, all right? I do want you to try to do these by hand because you will absorb the material better if you actually experience it, all right? Not just hear about it or look at it, all right? But do print maybe several of these to spare yourself, all right? Look at this table next. We'll discuss method number 1 here. If you get a graph in 2 dimensions, by generating your own dots, right? Generating your own ordered pairs, generating your own coordinates, okay? So here's a larger view of the same picture. Looks like this. I called it input and output because a lot of times this comes up as the subject of functions specifically and not just generally equations, but they are at least synonymous terms. Let me give you an example and change my slide here. Alright, get rid of that. And we'll go here. Alright, you know what, let me, since I'm hovering, let me point to this. Each of these headings here, these are different methods for graphing in 2D, right? 2 dimensions. Right? You can graph in 2 dimensions by generating your own points, right? Which again, if you're going to do that, I would encourage you to use these numbers as the input values for x, right? And then follow the order of operations, right? There's graphing in 2D by just using 2 points. If you're talking about bunny ears, if you're talking about a line at least, minimally you don't need 5 points, you just need 2. And then you could be very selective. You might find the y-intercept and similarly the x-intercept. We'll get to that. This is the most sophisticated of all of these methods here, right? Graphing by slope-intercept form. And even again, if you were using a calculator, you would really need to grasp this before you do that. It requires you to understand what a slope is and what a y-intercept is. We're going to get there as well. Anyhow, that is the 3rd method of graphing in 2 dimensions. Let's do the most brute force, which I would refer to this as the most brute force. Generating your own points. I'll have to use that in a minute. I don't have a moon here. I'm like, do not disturb. Not sure why I have that, but okay. Alright. When you're utilizing this method, whether because it's your preference or you're told to, right? The trick to it is that you have to make sure that you rearrange whatever the equation is that you are given, the line equation, right, to solve for x specifically, right? At least if you're going to use x as the input, right? That is the thing that you insert into the little machine that is an equation, perform the order of operations correctly, and then it spits out an output, right? I like to use that analogy because it feels very much like that as you're going through the algorithm here. All right, input, output, input, output. Give it something, it gives you something back. Working in the coal mine, coal mine, coal mine. All right, anyhow, we're going to practice this method, all right? We're going to start with a given equation and purposely, algebraically, rearrange it so that it works with this table. Right? So I'll write it in red for the sake of contrast. Suppose that you were given this equation, y minus 2 is equal to 2x, right? It's technically out of whack as it is given to you. Right? Y minus 2 equals 2x. I'm going to rearrange it algebraically and then stuff it right here just for reference. So how do I do that? All right? To solve algebraically is to get something alone on either side of the equal sign. I prefer the left personally. I think that's more practical. It usually is. All right? But it just involves opposite operations. So there isn't much to this. I'm going to draw a small little table here. All right. Pardon me, not solve for x. Solve for y. Dopey man. All right. Anyhow, that would be less work. All right. Y minus 2. If I want to move negative 2 from here over equals, all right, I have to perform the opposite operation. What is the opposite of subtracting 2? It would be to add 2 here and then add 2 here. Right. There is, by design, a cancellation effect, leaving just y so that it is solved for y, sorry, not x. And then there is some interesting stuff on the opposite side here. Now, they're not like terms. One has a letter and the other one doesn't have a letter. So you can't, legally speaking, you can't do much with them except sit them next to each other. So I'm going to write that here. Y is equal to 2x now plus 2. Right? It is the same equation, and this is incidentally called a line equation because of what it produces in terms of a picture graphically. Graph is a line, right? And it's set solved for y. So what we're going to do now to figure out in each of these 5 unique circumstances what the y value would transform into. Right? I'm going to rewrite y equals, and I'm going to emphasize the x variable as the input by just wrapping superficially a little parentheses around it. That is just to draw your attention to it. All right, I'll do this several times. The repetition of this is what makes a person remember it. So don't feel bad if this seems kind of redundant and maybe a little silly even. All right, it isn't. There's a purpose, I swear. There's a point to all this, a point. Okay, so if we now take these, again, arbitrarily decided, but still strategically decided, right? Because they're small, warm, fuzzy, and familiar, and easy to use. I'm going to systematically insert them in place of x, because that's what they represent. So you have 2 times negative 2 plus 2. Right? If we are just simplifying one side of an equation or another, right, then we're dealing with expressions, and therefore we follow the expression set of rules, which is the order of operations. And the reason why that is important to know is that the order of operations is pretty cut and dry. Which of these do you do first? The multiplication portion of it is what you must do first. All right. So 2 times negative 2, I'm just going to scribble on this, is -4, right? Then you have an addition or a subtraction problem that is left over, right? One of each sign dictates that you subtract. There's sign combinations decide whether you add really or you subtract really, right? So if you have one of each, as you would in this case, a -4 and a +2, you subtract to arrive at the digit, right? So 4 minus 2 would be 2, and then you assign a positive or a negative to this outcome based upon which has a larger magnitude. Magnitude is a fancy way of saying the size of the number, right? The distance from 0 is the official definition, but I think you know what I mean, right? The negative is larger in magnitude, right? So the outcome will match that, right? Without involving a drawing. If you write these two things together, let's see if green is cooperative today, you would have your first dot on the coordinate plane, which is -2, -2. So you have -2, comma, -2. Right? That looks like it's basically visible. I'll stick with it. Maybe that one will be better later. We'll see. All right. Next one. -1. Let's insert a -1 here and do the same thing. If I'm sticking with just the right side of this equation, I'm simplifying the expression that is there. And I'm following the order of operations, which dictates that I must do the multiplication first here. 2 times -1 is -2 in this case. One of each sign I must subtract to arrive at the digit. What is 2 minus 2? 0. And insofar as sign is concerned, it is irrelevant because 0 is neither here nor there. Right? It is neither a negative nor a positive. So the second point would be these things paired together. -1 and then a 0. 0, you see how this is getting easier and easier. If I use 0 in place of x, what is 0 times anything? 0, right? It goes away, essentially. Right? This is the power of 0. It's very useful for that reason. What are you left with? 2, and it would be a positive technically, so we're going to pair them together as 0, +2, and then next one is 1. 2 times 1 is 2, which is a positive. They're the same signs. The same signs dictates that you add. If they were both negative, you would still add, but they're both positive. So again, same signs, the combination dictates that you add. One of each, you subtract. Right? 2 and 2 is 4, and it's a positive, so you end up with this. 1 comma 4. At this point, if you want, you don't have to write the sign positive. Math people tend not to write those. It is an option that you have. If I were a good guy, maybe I would do that anyway. But it is implied that they're both positive when they're not written. And the last one is 2. 2 times 2 is +4. Same signs again. You add when you have the same signs. You subtract when you have one of each. These are both together added to 6. That is the digit. The sign of the answer matches the bigger one, bigger magnitude, which in this case is kind of irrelevant anyway because they're both positive. So you have a +6. So this is what you end up with. 2 comma 6. All right. So what is in green here, these ordered pairs that we have ourselves by brute force generated, we're going to put onto a coordinate plane and see what the pattern looks like. If we've done the calculation correctly, they'll be aligned, right? Since this is a line equation, that would make perfect sense, right? So I'm going to move this and put back the coordinate plane and graph those points. I'm going to erase the gobbledygook because it's in the way, and just leave those coordinates those ordered pairs to for reference while I'm doing it. While I'm plotting dots. Remember, plotting is dotting. Putting a dot on a plane. Right. So I'm going to use blue just because it seems to stand out pretty well. The first point, right, is a -2 for the x value and a -y for the y value. Remember, you must always move the amount that is x first and resist the temptation to make a mark until after you have moved the y amount second, right? At least when we're talking about ordered pairs, things that are wrapped in parentheses separated by a comma, all right? So, let's see. Go to the origin, which is this point again where they cross, and move -2. Now, since x decides that you move left or right, which direction would be appropriate if we're talking about a negative? Left. 2 increments, so it'd be 1, 2, and then we move the amount y, which coincidentally is the same number, but it's going to be up or down, depending upon what is given. So if it's -2, from here, we're going to go down 2, 1, 2, and now we make a mark, right there. You could, if you wanted to, label this particular point -2, -2, but it can get a little messy after a while, so I'm gonna resist the temptation to do that. Okay, that is the first one. Right. Here's the second one, -1, 0. From the origin, you go back to the origin, and you go -1, which is left 1 increment there. 0 is neither up nor down, so you stay put, and you put a dot there like so. Right. Next one, 0, +2. We'll go to the origin again. 0 is neither left nor right, but +2 is up 2. So you go 1, 2 when you have a dot there. And already you can see that they are like the planets, right? Aligning, sort of, it looks like. All right, next one, 1, 4, back to the origin. All right, 1 is over 1 space, and 4 is up 4. So 1, 2, 3, 4, and you have a dot here. And the last one is 2, 6, back to the origin, 2, 1, 2, and then up 6. 1, 2, 3, 4, 5, 6, and you have a dot like that. All right. Now what you should do, especially if you're doing this by hand, is get a ruler. Don't do it freehand. I mean, it is easier the more dots you have, but if you're like me, you kind of stray, without the edge. So I have my oversized T-square for sheetrock that I'm going to use here, just because I have to sort of, I feel like I'm like really, really tiny, and I have to, work with, big things, like as if I shrunk and I'm living in the real world here. So, just hold on to that. Try to very anal retentively, because being anal retentive in math world is always to your benefit. Line this up as perfectly as possible. There's a reason for that, right? And I'm going to draw a line through these points. And I'm going to purposely overextend the line past where I actually drew dots, right? Because if you do that, first of all, if the calculations are correct, and they should be, right, then you see an obvious pattern of linearity here, right? There isn't some stray dot. If you saw some stray dot, that probably means that you fudged the calculation somehow. Maybe you didn't follow the order of operations. Maybe you just screwed up a sign somewhere. All right. Anyhow, if everything is all well and fine and dandy, all right, no stray dots. All right. What you can do, if you were called upon to do so, is then predict what other coordinate pairs would be without doing the calculation, because the picture will tell you basically where the red line crosses the grid lines are the points. What is a line really but just a bunch of dots that are really close together? Right? Ponder that. All right? It's true. right? A line is just a bunch of dots that are really close together, right? It's a pattern. Anyhow, these have a name, this situation going on here, right? Dots that are basically in alignment are called collinear points, right? Those that are aligned, right, are collinear points, right? Now, in the old days, right, way before graphing calculators, and I really must encourage this as well, what your professor, your teacher, or whoever would encourage you to do is to label the drawing, because you might do several lines on the same graph paper, and I still conform to that, right? So no one's going to beat you if you don't do that, but you know, it's a good habit, right? Preserve the old ways, right? Don't just throw them away, right? That's silly, right? I'm going to write the equation as it was originally given to me, right? Which was out of whack, granted, but it's still useful. Y minus 2 is equal to 2x, right? If you wanted to write it in its slightly more convenient form, which is slope-intercept form, you'll see later, it would be this. Y is equal to 2x plus 2. What is written in red and what is written in blue are referring to the same line equation. It's just written in two different arrangements, right? Two different styles, if you will. This is as it was given. This is the way that is maybe more popular. Anyhow, this process of overextending the line for the sake of predicting points that are beyond where you actually calculated, right? There's a name for that. Right? You're not really responsible for that, but it would be good to have that vocabulary, I think, just to be a good person. All right? If you were to predict a point beyond where you calculated, this is called extrapolation. Impress your friends. Go home at night and tell your family, I'm extrapolating, right? I'm predicting things that are beyond where the data had come, where it ended, right? Extrapolation is predicting a point beyond these calculated points, right? If in theory you use the line, to calculate a point in between, right? There's a word for that as well. You know, that expression is an apt for that, but there's a word for that. There's the points in between that are predicted by the drawing rather than the calculation or data, all right, is called interpolation. All right, again, impress your friends with your elegant vocabulary, right? Extrapolation, extrapolating, right? Interpolation, interpolating. I'm going to interpolate. That is to find something between what is calculated, right? Extrapolate. That is to find a point that is beyond what is calculated, either this way or that way. I need some water, so I'll be right back. Okay. One other thing I'll add here, and there's a lot of mess, so I'm going to erase a bit. What you will see with enough experience doing this stuff is that there are sort of telltale signs that you're going to get a graph of one type or another, right? What I refer to as, this is again, you're not really responsible for this, but you could definitely handle it, right? What I refer to as first degree equations, right, which is decided by the degree usually of the input, there's a 1 here, I'm back sleepy. There's a 1 attached to the x. Look for that. Right? These produce, at least if it's like as part of an equation y equals x, these produce lines, straight lines. Okay? What you begin to realize after a while is that if you just, for lack of a better phrase, if you just sort of play math god for a moment, not to be blasphemous, and you just change a number here or there, you manipulate the drawing, right? And you know that from following the order of operations, and you're getting deep into the minutiae, the details, right? But anyhow, if you had something that was degree 2, second degree, in which case the only real alteration would be that there would be an exponent of 2. Normally we don't bother even writing 1, right? Right? If you have a degree 2, if this was part of an equation y equals x2, this produces another unique graph, right? Your powers expand, so to speak, right? If you want to just produce lines for whatever reason, all right, you stick with degree 1, and that's really all that you're responsible for. But if you wanted to extrapolate on this idea, then if you just up the ante to 2, this would produce something that you've probably heard of, which is this sort of hybrid U-V shape, all right, known as parabola. It's kind of a bowl, all right, parabola, all right? Just changing that number, all right, produces a very drastically different picture, okay? So realize the awesome powers that you have, okay? Math god that you are. Right. I hope you don't think I'm some kind of weirdo. You know, just sit at home thinking that they're really important when they're not, all right? Just for emphasis, you know. All right. Let me erase this. And we'll move on. All right. Looking again back at this slide, the overview. All right. This is graphing in 2D by generating our own points. Right. If again you were talking about a straight line, never mind a parabola or anything more complicated, how many points do you really need? 2. You don't need to do that much work is the whole point of this. And if the reason that I chose 0, and it is because 0 is very convenient, it's easy to use, then why not just strategically look for this point, which is known as the y-intercept, and this point, which is known as the x-intercept. This is basically using 0 exclusively as an input and using it twice, but in different places. All right. So the math, the actual arithmetic will be, you know, fairly easy. All right, but you got to be strategic too. All right, so to that end, here is another slide to discuss method 2 here. This is graphing using just 2 points. We're going to use 0 to find the x-intercept, and we're going to use 0 to find the y-intercept. All right. What does that entail? Well, you plug in 0 in 2 different places. If you're looking for the, somewhat ironically, x-intercept, you're meddling around with the y. When you're looking for the y-intercept, you're going to plug in for x instead. Right? One of the points that we had generated before was an x-intercept coincidentally, and one of them was a y-intercept coincidentally. Right? Now we're going to purposely look for those 2 things by plugging in here and there with the same number, 0. Right. Now it is possible that you may have to rearrange the equation to solve for x. Right? Or you may need to rearrange to solve the equation for y. That is to get one of those letters alone on one side. all right, before you proceed. All right? When all is said and done, what you'll have is an ordered pair. Right? For y-intercept, all right, it's going to be 0, comma, whatever the y value calculates out to be. All right? For the x-intercept, it's going to be whatever that calculates out to be, comma, y, 0. All right? Here is a table to kind of get you going. A little scaffolding goes a long way. I'm going to give you an equation, and we're going to have to probably rearrange it. If you, in the case of using 0, plug in the number that is given 0 first, it might spare you from having to do too much algebra, but don't be intimidated anyway. All right. Here is the original equation. All right. I'm going to write it up here in red. All right. 2x plus 3y equals 6. All right. Maybe I'll put it here. That would have been smarter, right? 3y equals 6. All right. If we're looking for the x-intercept, we're going to stick 0 in place of the y. So I'll write this maybe in green here. Same thing. And I'll write this in, next to it, the exact same thing in blue. All right. 2x plus 3y equals 6. All right. And we're going to stick 0 in the appropriate places in this green and in this blue incarnation of the original equation. So x-intercept, 0 goes in place of y, which is right there. All right. Remember, when you substitute, that is, you plug in a value into a variable that happens already to be butted up against a coefficient, in this case 3, what operation is implied by that? Right? If even without having a dot or parentheses, it is implied when two things are pressed together that they're being multiplied. So what is 3 times 0 right off the bat? 0, which means that it goes away, right? Which means that this is really 2x is equal to 6. And now we're going to rearrange this to solve for x. All right? If I want to justify moving the 2 from where it is over equals, right? I have to perform algebra now. Opposite operations. The opposite of multiplying by 2 is to divide by 2, and to divide by 2 here. There is, by design, a cancellation effect. Right? In this case, 2 divided by 2 produces a 1, which you don't have to write. And then you have x is equal to whatever the outcome of 6 divided by 2 is, which is what? 3. Right? So x is equal to 3. If you're going to write that in the style of ordered pairs, and we just figured out the x-intercept, we have the value of x equals 3. So x equals 3 when y equals 2. I'll just re-emphasize that here. Okay, that's one dot. Now we need a second one. Right? If I'm looking for the y-intercept, I'm going to stick a 0 in place of x instead. So that is here. All right, and I put a 0 in here. Again, these two things are pressed together, so it implies that they're being multiplied. 2 times 0 is just 0. It goes away. You don't have to write it. And then you have 3y equals 6. Right? Again, because you now have to solve for y, you have to rearrange it, all right, to move the 3 from here to here. Right? When you're going over equals, you play the game of algebra. If you just stick it on one side or the other, that is, if you're just exclusively working on the left or just exclusively working on the right, that's arithmetic. Anyhow, we're performing algebra here. 3 times y. In order to justify it, we use opposite operations. The opposite of multiplying by 3 is dividing by 3 here. And then if you did that here, your hands are tied, you're obligated, you must perform the same operation here. So there is, again, by design, a cancellation effect, which is a 1 for the division. And that leaves you really just y equals the outcome here. 6 divided by 3 is 2, right? So I really shouldn't circle that. That is the second point. If we stuck 0 in place of x and we got 2, then our second coordinate, or ordered pair, is 0, 2, right? We need to plot no more than these 2 points in order to graph a line, right? So I'm going to go back to the graph paper and plot 3, 0, and 0, 2. All right, sip of water, please. All right, the first one, remember you do x first and then y. So 3 for the x from the origin is 3 to the right. 1, 2, 3. Consider what y is first. It is, that is, before you make a mark. It's 0, so it's neither up nor down, it's just stay put. You put a dot there officially. Right on the axis. Not a coincidence, that is on purpose. Right? Now we do the blue y-intercept. Do the x portion of this first, or at least consider it from the origin. 0 for left or right is neither left nor right. But positive 2 is up 2. So I'm going to go up 2, 1, 2, and then officially make a dot here. Okay. So I'm going to pull out the ridiculously oversized t-square and anal retentively draw a line again. All right. And again, you should be very twitty about this because it's math and it requires that. Right? By that I mean very precise. Again, overextend your line through those points and beyond. Right? You see a graph like this. Right? And I'm going to label it. What was given to us was the equation 2x plus 3y equals 6. Now, what is illustrated here is why the name y-intercept, why the name x-intercept. This is literally y-intercept, I'm going to just abbreviate INT here, is where the line crosses the y-axis. Okay, so aptly named, appropriately named. All right, y-intercept. This is the y-axis. All right, and as you might have guessed, all right, if you extrapolate here, all right, this is the x-intercept. This is where literally the same line crosses the x-axis. Okay. So that is the reason for those names. Anyhow, the point, pun intended, is that you only needed 2 dots, 2 points, in order to accomplish this task. If you had, again, a more sophisticated graph, like, degree 2, that is, the exponent was 2, and it ends up producing a parabola, you really would not have, this would get you only so far. It is useful, and it will always be useful, but it would not be enough in a more complicated case, right? For lines, which is all that you are responsible for right now, this is sufficient. Okay, so just remember that technique. It's very useful. Okay. All right, back to the overview again. Okay, you can graph by generating 5 points, you can graph by generating 2 distinct points, and then technically if you were going to explore this method, which we shall in a few moments, the slope-intercept form, that's when it specifically y is alone on one side, and then there are these key features on the opposite side, right? The thing that is weirdly labeled b, right, is actually the y-intercept. So if you saw a number here, let's just say hypothetically you saw a positive 7, one could infer that there's a point 0, 7 immediately, right? Anyhow, in terms of the number of coordinates that you would need in order to accomplish the task of graphing a line, this is 5 points, this is 2 points, and this is technically 1, right? So that would be the easiest, that would be the most efficient. You would need to figure out a second point at minimum, right? That is what the slope will accomplish, right? But the slope is not, even though it involves y's and x's and y's, it itself is not a ordered pair. So you kind of can deviate from which of these things do you draw first or you graph with first. All right, very often because it's y sitting on top of x, you end up doing the y portion of it first, but I'm getting ahead of myself. Anyhow, just realize that the y-intercept is what is involved in the slope-intercept form, not the x per se. All right. Now, to explain this a little bit more thoroughly, let us talk about slope for a moment. All right. Okay, I'm going to just sort of get a blank white screen for a moment, so I'm going to just open a PowerPoint as I can get that. Okay, let's talk about slope, all right, just by itself. What is slope, all right? For all intents and purposes, slope is a ratio, right, which is a fancier way, it's really a more general way of saying fraction. So you might say it's a type of fraction, right? It would be better to call it a ratio than a fraction for some certain reasons, all right? It's less strict, all right? Anyhow, a ratio is just a fancy way of saying a number sitting on top of another number, all right? Again, what we think of as a fraction, all right? Now, what is above and what is below? The top of the ratio, that is known as slope, right, is representative of a change in y, meaning up and down. That's an e, I swear. All right. What is the denominator, or the bottom, really? The bottom of this ratio, that is otherwise known as slope, all right, is the change in x, which is again a dimension of left and right, horizontal and vertical, right? There are mathematical abbreviations, right, that are often used, and I don't want you to be intimidated by them. That's the only reason I mention them, right? You've probably seen them, right? It looks like this, all right? If we're talking about a change in y, you might just see this Greek letter known as delta. Right? It's a capital Greek letter known as delta. So if we're talking about the change of y specifically, you will see a triangle and then you will see a y. Right? If we're talking about a change in x specifically, what you might see is a delta and then an x. If we were talking about the change in, any symbol, happy faces, then it would be delta happy face. If it was a hieroglyphic bird symbol, a change in hieroglyphic birds, it would be delta hieroglyphic bird symbol, right? Whatever is next to it is the change in. Now, mathematically, what does that mean? I'm going to put this here because I have more space. It literally means subtract. Right? So if the top is changing y, and alternatively we could have it as delta y, and the bottom is changing x, and we could write that as delta x, then all it is really is y minus y and x minus x. To distinguish one from another, we incorporate subscripts. Remember, subscripts are not an operation, they're just a label. All right? They're a smaller font usually and a little lower, right, than the usual tier. What goes in front is a 2 here and a 1 here. In a physics textbook, what they would do instead of having 2 and 1 is they'd have an F and an I. Final as in last and initial as in start. All right, anyhow, this is sufficient. Subscript 2 is subscript 1, subscript 2 is subscript 1, meaning that there's 2 x's and there's 2 y's. Where do they come from? They come from 2 points. 2 given, assuming, points. So you'll have x1, y1, and hopefully x2, y2. My red is starting to die. All right. Bad behaving marker, go away. This is the slope formula. Which, again, if you don't like my explanation, and I would never get mad at you for that, here it is, swiped from the textbook on this sheet, nice and neat. All right, vertical change, horizontal change, they call it, and there's the formula. One thing you might notice is there's this other letter here. Now, I don't know for sure, to be honest, right? But if you were referring to the end result here, the actual number that you get from doing this calculation, that is using this formula, it is like y is weirdly abbreviated b, this is weirdly abbreviated m, right? I don't know why. I'm not sure. I can only speculate. All right, now bear in mind, this comes from the early 1600s, right? All right. Rene Descartes is intimately responsible and connected to this subject of a coordinate plane and these features. And he spoke French, right? And when he went to college as an educated person, he most likely studied Greek and Latin, right? Perhaps, again, I'm just guessing, perhaps in French or Latin or maybe even Arabic, right? Because that's where algebra really comes from, all right? At least insofar as the Europeans are concerned, they got it from North Africa, right? Perhaps that in some other language, slope, the concept of slope is the first initial is not an S, perhaps it's an M, right? Same thing with y-intercept. Anyhow, we would need to calculate by subtracting first, subtracting second, and dividing last, right, this formula in order to calculate slope. All right. Now let me show you what is possible when you've done the calculation. You'll see maybe one of 4 things. I'll draw a little diagram. There are basically 4 possible slopes to be aware of. I'm going to try to make this neat, so I'm going to use again, t-squared to make a straight line for once. And try to confine myself like so. For the sake of this diagram. All right, there's 4 possible outcomes as a result of doing the calculation. Maybe I'll just move this for, well, No. I'll leave that alone. I use green to just draw a coordinate plane here, x and y, and then a second one here, x and y, and then a third, x and y, and then a fourth, x and y. And here's the origin, the origin, the origin, and the origin, right? This is going to harken back to what I was mentioning before. The Roman numerals, that is the quadrant regions, as they're labeled in Roman numerals. It would be good to know them when you're trying to get an inkling about what the slope is, right? At least if you're just staring at a drawing, never mind the calculation. If you have a line that basically runs like so, right? It could be running like that, like this, somewhere in between. What is basically from the third quadrant to the first. This is a positive slope. That is the way that the fraction or whatever the calculation works out. You're going to get a positive number overall, right? Positive fraction, or a whole number technically, right? If on the other hand, you have the incline of this line running something like this from what would be the second quadrant down to the fourth, this is a negative slope. Right? Again, you don't need to do a calculation in order to guess that. Right? As long as you have this fundamental information memorized, or at least have a reference to look at. All right. If you see something that is pitched basically running this way, that is from the second to the fourth quadrants, then you have a negative, right? This is another dud on the way out. If you have something on the other hand that is perfectly horizontal, notice that these are diagonal lines in varying incline, and this is diagonal, and this is perfectly horizontal, which could be here. It could be running right on top of the x-axis, or it could be below it. If these are horizontal lines, then the way that the math works out, the calculation, is that you end up with actually zero slope. That is that m equals 0. Okay? The reason being that if you put in the same y values, you would have 0 above the line. So you'd be dividing into 0 technically. Then there's this scenario. Right? You could have a perfectly vertical line, which again, it could be running over here, right on the axis technically, or on this side of it, vertical lines. The way that the math works out, the calculation, is that there is what you would refer to as an undefined slope. Now that to me is somewhat counterintuitive, and oftentimes the textbook will say, what's synonymous with undefined? No slope. But I don't like saying that for a couple of reasons, and not the least of which, people think of no as in nothing and nothing as in 0. You don't want to confuse this situation with this one. They're unique. They're distinct from one another. So you would say in this situation, if you have vertical lines, for sure, this is undefined is the best way to refer to it. Right? It's limitless. Right? When you think of incline, you think of something diagonal, really. All right? And it starts at 0 and then it inches upward, right? Like so. Anyhow, this is undefined. What is the reason for that? If you examine the minutiae, that is the fine details of the calculation, the way that the math works out is that you would have some number above the line, and then 0 as a denominator. This is a mathematical sort of no-no, where you have basically a number divided by 0. To do that, you go directly to math hell, right? Right. If you ever, even if you were playing around with your calculator and you divide it by 0, you would get an error message, right? You can't divide by 0, right? It's a mathematical impossibility. On the other hand, the way that this calculation works out is that the situation is exactly reversed. You would end up with 0 on top, and you're dividing by a number, right? This is dividing essentially into 0, which is not the same thing as dividing by 0, right? This is the divisor. This is the divisor, some number, all right? Dividing into 0 is perfectly fine. You're going to get 0 as an answer, right? It's a mathematical possibility. But dividing by 0, you can't do it, right? It defies logic. All right. Now, having said that, let me give you a unique pair of coordinates, and we'll discuss how you can get it visually versus a calculation. I'm going to get out of here and move on. Quit. All right, going back to the graph paper. All right. Let me erase this. Does that look like it isn't maximized? Because it isn't. Alright, there we go. Alright, suppose that you were given these 2 points. I'm going to put them in green, sorry, I hope that is visible. -1, -3, and if it isn't visible, I'll rewrite them. And 1, 5, right? Fresh sheet of coordinate plane here, right? Graph paper with axes, right? Let me start by putting dots for these 2 points, right? There would be, for this one, maybe this would be a little easy to see. For -1, -3, -1 would be to the left, and -3 would be down 3. So 1, 2, 3. You'd have a dot here. All right. And for this one, 1, 5, you'd start at the origin again, you go over 1 and then up 5. So 1, 2, 3, 4, 5. All right. Again, I'm going to very, very carefully take a ruler and connect these 2 points, and in fact overextend the lines. So if I do this precise, and I should, you'll see a nice pattern here. The beauty of doing this on graph paper is that ideally the boxes are a way of figuring out what the slope is without using the formula. You don't need a calculation in order to figure out what the slope is. What you would need to do is draw an imaginary right triangle. And it would have to be a right triangle, connecting the points. To do that, I'm just going to use maybe red, because I think it just contrasts a little bit easy to see. I don't want to confuse what I'm going to draw with the actual line here, which is in black. If I draw an imaginary right triangle connecting these points, I'm going to draw a dashed line like this until I'm just on the same tier as this red dot. And then I'm going to draw a little line like this over here. All right. Anyhow, this is called a right triangle because it has a 90-degree angle here. A perfect 90-degree angle, which you don't have to get out a protractor and measure. It's on graph paper, right? It would be cool if you did that, but it's not expected of you. All right, anyhow, there is an imaginary right triangle connecting these 2 points, as you see here. Now, again, if you did this on graph paper, you could use the boxes. I moved it back. How did I do that? Figure it easy. All right, anyhow, somehow I moved it. There you go. If you count the boxes from here until there, right? How tall is this imaginary right triangle? 1, 2, 3, 4, 5, 6, 7, 8. This is the change in y, otherwise known as delta y, right? It's 8, right? 8 boxes that way. If I count the number of boxes from here, this is a little bit more narrow naturally, from here to this same corner, that would be the 90-degree angle, how many boxes wide is it? 1, 2. This is the change in x. And it's only 2 blocks that way and 8 blocks that way. Now, I'm going to do the calculation in a moment just to verify this, right? But we have the information from just staring at the picture already. We really don't need to do the calculation. It's just good to be able to have the mental flexibility to do it one way and another. Anyhow, notice that there's this triangle symbol. It itself is not a right triangle, it's a delta, really, right? But it resembles that. I can't help but sense that René Descartes and his contemporaries probably elected to use this symbol because of the reference of a triangle in the picture. Anyhow, if slope, otherwise known as m, weirdly, is a change in y over a change in x, then we have the numbers that we need to figure that out. So it would be 8 sitting on top of 2. All right, what's 8 divided by 2? 4. All right, the slope is 4. All right, positive 4. Now, if you did the brute force calculation, which again you should be able to do, all right, that would verify that this is correct. All right, so I'm going to move this, all right, and walk you through that process. All right, I'll use black because I think it is a little bit easy to see. All right, the formula, all right, is this. M is a difference in y's over a difference in x's. Right? D as in delta. Delta is the Greek letter for, Romanesque D, right? And delta, D is in difference as in subtraction, right? So, these granted -1, -3, that point, and 1, 5, that point, are not labeled with subscripts. So you have to take the artistic license yourself to label them as such. It doesn't matter if you make this the set of 2s and this the set of 1s, or vice versa. But be consistent. As I'm fond of saying, in math, you can get away with murder as long as you are consistent. So I'm going to, for my own sake, right, I'm going to label this x1 and y1 only for the reason that they show up first, right, in this writing. So therefore, this would be x2 and this would be y2, right? I'm now going to superimpose them in the calculation. And we'll see if we get the same figure. All right, y2 is the number 5, right, up above this line here, minus y1, the subscript 1, is a -3. Do not confuse the negative that coincidentally happens to be part of the formula here. So there's a minus in the formula, and then there's a -3 adjacent to it. All right. Down below, there is x subscript 2, which is 1. There's a minus in the formula, and then again, coincidentally, there's a -1 in this figure here. So it is adjacent to it. Now, because it is getting a little bit messy, I'm going to remove the graph paper for a moment. And go back to maybe PowerPoint because it's a nice white surface. Okay. And what we have here is 5 minus -3 above the line, according to the formula for slope, and 1 minus -1 for the x difference, according to the formula down here. All right. What happens when you have a double negative? Now, bear in mind, the double negative is in between numbers. When you have a double negative between numbers, there's more or less a cancellation effect. So if you want to think about it in a sort of verbal way, it's like speaking in double negatives. To say that you ain't done nothing, for example, technically is an admission of guilt. All right? If I was playing with matches as a little kid and I said, I ain't done nothing, Grandma, technically it means, yeah, Grandma, I set fire to the house. It's an admission. It's not proper English because it's a double negative, all right? All right? Anyhow, when you see double negative like this, it really translates to 5 plus 3 in this case. These become a positive. That's just a funny looking 5, right? Same thing here. A negative next to a negative immediately, no number in between them, is really 1 plus 1, right? Anyhow, what is 5 plus 3? By no coincidence, it is an 8, all right? What is 1 plus 1? Similarly, by no coincidence, it is a 2. What is 8 divided by 2? 4. Now, last thing to emphasize about this. 4 is the most concise way of writing the slope, right? But it is really an alternative to what we had drawn, right? It is a positive 4, right? You could, if you wanted to, keep this in the style of a fraction because it is often more practical when you have it that way, in which case you could take 4 and you could just stick a 1 under it, okay? If it is a positive, I have the tendency to just sort of put that attached to the top. It isn't wrong if you put it as attached to the bottom, but remember that it really is one or the other, right? In the case of a positive, it wouldn't matter, but if you had a negative, just say hypothetically, if you had -5, all right, you could make it -5 over positive 1, or you could make it positive 5 over -1. That is perfectly legal. It's one or the other, really, right? Because overall, it is a negative in this combination when you're talking about multiplication or division. Now, let me get back to the graph paper because I want to show you another thing. Okay, now here's a drawing, and I'm going to get rid of this junk that is next to it, because it's taking up too much real estate here. And I'm going to remove this gobbledygook here. And I want to point out something. We could, in a case like this, choose the simplified incarnation of 8 over 2. the simplified incarnation of 8 over 2 would be 4 over 1. The relationship between the top thing and the bottom thing is the same using these numbers as it is using these numbers. Right? That's what usually drives people nuts about fractions, and it's part of the reason they don't like them. Right? Because like 8 and 2 are two different numbers. Why would I want to use anything else but those two things? Think of them not as the individual parts, but the whole that they comprise. All right? Anyhow, if you examine this triangle here, the pattern of 4 over 1 means the same thing visually. Here's what I mean. I could draw a smaller right triangle that has the same proportions overall in this picture, and I'll do it in blue. It has to be on the grid lines and on the lines. So I'm going to say if I start here and I draw an imaginary right triangle down to that edge and then connect it, how many blocks wide is it changing x now? Just 1. Right? How many blocks tall is it? 1, 2, 3, 4. That is not a coincidence. And this pattern will continue into infinity. Over 1 up 4, over 1 up 4, over 1 up 4, forever and ever and ever and ever. All right? Or backwards, to the left 1 and down 4. All right? To the left 1 and down 4, to the left 1 and down 4. You see the pattern, right? Straight lines have this consistent slope. Right? Curves, on the other hand, have a changing slope, which is why calculus came about as a subject. Calculus came about as a subject because we're trying to basically figure out the slope of something that isn't consistent. A curve has a slope, but it changes at each individual point, infinitely, right? Infinitesimally. Right? Anyhow, this is foundational information, and this is all that you're responsible for. Right? Just realize something. If you do it visually, right, that's great. But you have to have it memorized what the orientation of the line would be in terms of a sign, whether it's a positive or a negative. Right? That's why I'm just going to show you my own little sketch here. It would be good in the long run to memorize that if you're running vaguely from the third dimension to the first, you are indeed a positive. That is basically what's happening here. It's just very narrow, right? If, on the other hand, you had something that was running from the second quadrant down to the fourth quadrant, just realize that unless you do the calculation, it's not going to tell you that it's a negative overall. You have to know that. Right? Memorize that information. All right, here's the overview one more time. Last method of the three that you are responsible for. Right, we have delved deep into slope-intercept form territory. Right? We understand the concept in theory of a y-intercept. Again, it's just weirdly labeled b. Right? And that represents a coordinate, an ordered pair of 100% of the time 0, and then whatever unique to the problem, the b value is the y value. The slope, on the other hand, is not an ordered pair. It just involves ordered pairs, unfortunately. Nonetheless, it is a powerful, potent thing to have, to wield, because you can get as many points infinitely without having to do any calculation, especially if it's given to you. Right? So let's do an example like that. Right? And to that end, I made, again, yet another scaffold here. So we'll talk about that. There's this. If you were going to graph this way, book here. Suppose that you were going to graph employing the slope-intercept form of the line equation. All right. Suppose that you are given this equation: 4x minus 3y equals 9. All right, now what you may have to do sometimes is rearrange it to start with. Rearrange algebraically, which is opposite operations, right, to solve for y specifically. All right, the slope-intercept equation of the line, form of the line equation, is, notice, distinctly y equals. The y is sitting by its lonesome on the left side, and then the interesting features, the slope and the intercept, are on the right side. Right? That is by design. And if you're going to go about a task this way, you must conform yourself. Right? Now look what is written in blue here. This is all messed up, right, on purpose to go through the mental exercise that this entails. Right? So notice where the y is, notice where the x is. It would seem to me that if you're going to rearrange this to get y alone, the way to go about that is to move 4x over equals. So I'm going to draw a little table like I've been encouraging you. What is the sign of this 4 if it's not written? What would you assume it is? Well, if it's not written, one would always assume that it is a positive to start out with. Right? If you want to take the whole term, that is the whole chunk, that is the 4x term here, and bring it over to the opposite side, you just are going to add or subtract. Right? So if it's positive on this side, to justify moving it, you're going to subtract, and do indeed bring the letter with you. Right? I know normally you don't bother to do that, but you would in this case. Right? 4x minus 4x, and then you would write it over here, just temporarily. Anyhow, a person at this point might get a little annoyed, right? And they would say, hey, I don't know what 4x is, so how do I know what this gobbledygook is going to work out to be? Convince yourself that by sheer logic alone, right? Even if I don't know what the value of this is, it doesn't matter, right? What is something minus itself? What's 7 minus 7? 0, right? What's 0 minus 0? 0. What is 2 minus 2? 0. Anything minus itself, mysterious or not, is by sheer logic alone a term that is going to cancel. Right? So what does that leave you with? Minus 3y. And then, because I'm trying to be a good guy, I'm going to purposely arrange this junk over here, this blue 9 and this red minus 4x, in a particular way. According to the model, the x portion of the show here is really what you should write first. So I'm going to do that. Right? It isn't wrong if you write it backwards, all right? But since they're like terms and I can't really legally subtract them, the most that I'm going to do is park them next to each other. So this is technically a positive 9. All right? Now one more step and then we can start plucking out the relevant information. There is still a hanger-on here, a 3, that is minus 3, all right? And I want to get it to be just y equals, not something with a coefficient. If I want to continue with this process of moving stuff around algebraically, and I therefore want to move negative 3 from where it is over to the opposite side, because again, they are butted up against one another, the implied operation is that they have multiplied to start with. So if I want to justify moving it, I have to divide by negative 3 here, and then be consistent. If you divide it on the left side, you are obligated to divide on the right side, both parts. That is, this gets a negative 3, and this gets a negative 3 under it as well. These cancel, becomes 1. A negative divided by a negative is a positive when you multiply or divide. And then you're left with this. Y is equal to negative 4 divided by negative 3. Now for your own sake, combine the signs. A negative divided by a negative is just a positive, so this is really 4/3 with an x attached to it. Excuse me 1 minute. this portion of it is a positive 9 divided by a negative 3. So the sign combination of one of each when you're multiplying or dividing is different from when you're adding or subtracting. Remember that positive divided by negative is a negative overall, and then 9 divided by 3 is just 3. Right? What we're going to do is now pluck out the relevant information. Right? We're going to take this fraction, that's usually what the slope looks like, and we're going to take this number negative 3. Right? Negative 3 is, again, standing in place of b, which is the weird label for y-intercept. Understand that it is the coordinate 0, comma, negative 3. Right? The slope is, the way that it works out mathematically in terms of its sign combination, is 4 over 3. Right? So that means that when all is said and done, this is going to be 4 up, and positive 3 down here would be 3 right. Now, because a slope is not a coordinate pair, an ordered pair, you can deviate from the norm, which is that you must deal with the x thing first and the y thing second. Ordered pairs must conform to that. Slopes, you can get away with doing one or the other first. I have a tendency to do the y myself. All right. Anyhow, this is not a point. It gets you points. So we're going to graph this first, always first, and then we're going to do that second. Let me get some graph paper. And we'll move on. Okay. I'm going to erase this. Good. All right. And blow this up just a wee bit. I'm going to always start with my actual point, 0, negative 3, which just coincidentally happens to be right where I need to work. 0 is neither left nor right, but negative 3 is down. So I'm going to go 1, 2, 3 and put a dot proudly here. All right. When you are using a slope, start where you left off. Right, which is namely the y-intercept, from the y-intercept. So, from this point here, rather than the origin, again, 4 over 3 is the slope, and yes, it came from ordered pairs, but it itself is not an ordered pair. It's just something you use, a tool, to get an infinite other ordered pairs. So start from here where you left off rather than the origin when you're using a slope. All right. Again, you could use the 3 portion of this first or the y portion of this first. I have a tendency to read up the top first and then the bottom second, but hey, it doesn't matter. I'll show you. All right. Positive 4 is 4 up. So from here, 1, 2, 3, 4. Resist the temptation to make a mark. All right. And then go 3 to the right. All right. 1, 2, 3. Right? If you did the bottom first, from here, 1, 2, 3 to the right, and then up 4, 1, 2, 3, 4, it lands you in exactly the same space. All right? And if you want, again, this is the beauty of slope. It itself is not an ordered pair, but it could get you an infinite number of them. You just keep following the pattern because we're talking about a line, and a line is consistently that slope. So up 4, 1, 2, 3, 4 over 3, 1, 2, 3, dot here. Up 4, 1, 2, 3, 4 over 3, 1, 2, 3 here. Right? You could go backwards, but you'd have to use both negatives in that case. All right. Left, negative 3, down, negative 3, 1, 2, 3, 4, and so forth. All right. As in all cases, or at least initially, what you should do is get a ruler. Don't do it freehand. All right. Especially if you're like me and you have sloppy, jittery hand. And connect the dots. And you will see that there is a collinear pattern here into infinity. All right, there's your line. So, again, be a good guy or a girl or person, all right, and label it according to, again, this is just preserving the old ways. You know, write the name of the equation as it was given to you. So if it was, botch of the loop, that's fine. It's 4x minus 3y equals 9. Okay. Or you could write it in the newfangled incarnation of this, which would be what? It would be y equals 4/3 x minus 3. Right? It is in this form, in the slope y-intercept form, that it is most practical to graph, especially by hand. But even if you're using a calculator, a graphing calculator, and you guys in MAT-114 and 113, you're not really supposed to, right? There's a button on the calculator that is specifically y equals. Why? So then, how come? Because then you could enter things in that style, right? And it will draw it for you. Anyhow, you're here because you need to learn how to do this the old-fashioned way, so don't resist it, right? Don't make a machine do this for you. You need the experience. If you don't go through the experience, it's like getting a gym membership and then sitting there and eating donuts all day, all right? Do the work. No pain, no gain. Right. All right. All right. In terms of the equations of lines, there's really three that you might see. So let me turn off the projector for a moment, give the bulb a rest. I don't really need it. And then open the curtain here. Come on. All right. I feel like a goblin. I've been living in the dark. Light. All right. I don't know why am I casting too much of a shadow. There are three basic line equations. That you may see. Right. The more obvious type, the more likely, is those that are for diagonal lines. Right, that's the normal situation. Right. And again, it's usually like this. It's usually in slope-intercept form. It can be out of whack, and requiring a little rearranging perhaps, but it's usually y equals mx plus b. All right, in which case, you'll notice, all right, it has both a y and an x in it. Right? There's a y here, and there's an x here. Right? That's the normal situation. All right? If, on the other hand, all right, you have what is simply a horizontal line, the equation is simplified. A horizontal line is, it's really just going to be, ironically perhaps, y equals some number. It's just y, right? There isn't an x involved in this. The reason being, right, it's because what is the slope in the case of a horizontal line? The slope is equal to 0. So if you put a 0 here, 0 times whatever the x value is, it's going to just cancel out of existence, and you're just left with the number in the horizontal case, right? If, on the other hand, you have the other possibility, which is that you have a vertical line, this is again a dumbed down, slimmed down version of this. It's going to be, again, somewhat ironically, just x equals a number. All right, and the reason is because, all right, the slope is undefined in this case, technically. All right, remember, if your slope is undefined, all right, then we're not going to consider it. the equation would really just be this rearranged. It would be x equals something. So if you move the slope over there, it would end up being undefined and we won't consider it, right? Anyhow, so if you're looking for a formula as basically a launching point, a model, right? Save this because this is pretty much the normal situation, y equals mx plus b. But if you realize that you're working with a vertical line or a horizontal line per se, this is the model here, right? Y equals a number, x equals a number. Let me get some water. Now let me give you a drawing and we'll decide whether we're doing this, this, or this, and we'll pluck out the information that is needed just visually. I may have to turn off everything again. That is to say, without doing a calculation, we could get a line equation. Are we on time? Okay, we're good. I'm going to draw this on graph paper because I think it would be better. So let me turn the projector back on and move that up. Okay. Suppose that you had a drawing, wake up, that looks like this, right? That is writing, we have to write a line equation, right, given a drawing, right? That is a graph here. And to that end, I'm going to take out my ruler again and very strategically try to emulate what I have here in my notebook. All right, let's see if I get this right. I'll pitch it slightly. That looks like it's okay. It's not beautiful. All right, couple of things to ask yourself. All right, is this a diagonal, horizontal, or vertical line? All right, because that will decide what model we're going to start with. All right. I would say, although it is rather shallow in terms of its incline, that it most closely resembles a diagonal line. So kind of the usual situation, and therefore it is the more involved model, which means that we're going to utilize y equals mx plus b, all right, that model. All right, which means what then? It means that we need to pluck out two pieces of information. We need to know what the slope is, and we need to know what the y-intercept is. Y-int and slope only. Okay, now if this is drawn on graph paper, then our task is pretty easy. All right, we'll go for the slope first. All right, I'm going to put a dot right here to emphasize, because this is evidently where the line, that is the black line, crosses the y-axis, so therefore it must be the b value. All right, what are the ordered pair? What are the coordinates of this particular dot then? This dot is 0 for x, because it's a y-intercept, and then it is up 1 from the x-axis, so it's technically 0, positive 1. That means that in the model, I would have to put a positive 1 in place of b. Right? And already we're making progress. That's great. Okay. The slope, on the other hand, is a little bit trickier, but we're going to utilize the technique that has been discussed, right? Which is that you try to draw a right triangle connecting points. Now, there is another point in here that is right on the grid lines, and that's really what you want. You want something that is drawn right at the point of intersection of grid lines, because it makes it easier to calculate. All right? So there's a second point here, which again, I'm just going to sort of emphasize this second point, which is in green. And technically speaking, this point, which was not specified by the problem, but I looked at it and figured that's what it has to be. All right, this is where the line crosses the x-axis. So therefore, technically, it is the x-intercept. Now, in terms of the formula, the slope-intercept formula, we don't need the x-intercept to be identified to fit it somewhere in here. But it happens to be a very, very convenient point. So as a habit, if I had to write an equation, I would still kind of train my eyes on these two places. All right? They're close and they're easy to read that way, especially if they're on grid lines. So I'm going to try to draw an imaginary right triangle that is connecting these points. All right? And remember, this would be a change in y, right? From here to here. And this would be a change in x, right? From there to there, from that corner where the right triangle has one edge meets another, right? How tall is the y value? It's just one block tall, right? How wide is the x value, change in x? 1, 2, 3, 4. So if slope is a change in y over a change in x is really 1, that's the digit, over 4, because that's the x portion of it, then the fraction that is the slope is 1/4. I am going to jump the gun a little bit and stick the 1/4 in here because it does belong there. All right? That's the slope. Just gleaned from looking at the drawing, not doing an actual calculation. Now, the other thing is, we really do need to decide what the sign is, right? And just staring at the picture is not, like, we would really need to do the calculation if we wanted to validate a suspicion that we had, which is that, okay, this is a negative, right? Unless you memorize certain conditions. So I'm going to sort of bring you back here. If you memorize these conditions, that you have a diagonal line, a horizontal line, and a vertical line, and that if it's running from basically the second quadrant, however steep it may seem, over to the fourth quadrant, that it would have to be negative. Right? Then that would tell you what you have here. Well, this line does seem to be running from the second quadrant down to the fourth. It's pitched inclined that way. So therefore, this is, without doing a calculation, negative 1/4. Right? You could, again, perform the actual calculation to validate your suspicion. Right? But again, if you memorize or you have some kind of a reference, this is guaranteed. All right, I'm quite certain of that. I wouldn't tell you otherwise. All right, 1 down, 3. This is 1 down, so that's -1. And this is 3 from here to here, 3 to the right. So that would be +3. Pardon me, 4 to the right. So that would be +4. All right. Overall, what is a negative divided by a positive? It's a negative. Usually what happens is that in a textbook, they have a tendency neither to favor the top nor the bottom. I still feel when you're actually drawing it, it is to your advantage to just do that. all right, they will just put the negative out in front, neither favoring top or bottom. If you do try to draw it from a fraction, do yourself the favor, just exclusively attach the negative to the top, and then you won't even have to think about it, okay? It's one or the other, not both, if it's a negative fraction, okay? The overall outcome of dividing a negative by a positive is a negative, okay? So what is the equation? Negative 1/4 plus, that is negative 1/4 x plus 1 is this unique black line here. Sorry, I'm not giving you the finger, not intentionally anyway. All right. I wouldn't do that. All right. You'd probably think it's, screw you, man! 2 hours. No, don't get frustrated. There's an explanation for everything. All right. Convince yourself of that. All right. You may not understand something entirely all at once, but I swear to you, all right, no matter who you are, eventually you could figure anything out yourself if you had to, right? It's just an endurance test, nothing more, all right? All right, let me turn this off, at least temporarily, and then we'll continue here. Let me walk you through a word problem, and then we'll be done for section 6.6. Now, here's an interesting thing. What you'll see is when there are applications for this material, the applications employ, all right, a model, all right, and the model is, usually it's the slope-intercept form of the line equation, y equals mx plus b, all right? So realize that you have that tool, that familiar friend, to get you where you want to go. That's the vehicle. Right now, in terms of the picture, though, right, Math World is anything that is possible. Right? Math World, to give it a name, is what? It's 4 quadrants. 1, 2, 3, 4, like Rocky movies here. Labeled X, Y, and here's the origin. All right. This is, to emphasize the point, Math World. At this stage in the conversation, Math World used to be 1-dimensional, but now it is 2-dimensional. And eventually, if you take calculus, it would be 3-dimensional. Right? And if you take a physics class, it's 4-dimensional, right? Or more than that if you're talking about quantum mechanics. Right? Anyhow, in real ordinary life, here on this plane of existence on Earth, Math World is shrinks, right? The focus of Math World becomes typically much more limited, right? There's still an axis this way, horizontal, and there's still an axis in theory this way, vertical. But the perspective changes to almost exclusively quadrant 1. So if Math World is anything that is theoretically possible, the real life application of this would be much smaller. Right? It's usually, typically, just quadrant 1 without really giving it a label. But think about any test that you have taken, any standardized tests, all right, they're usually a boring graph, right? That looks something like this. And they change the labels. Math people just label things X and Y consistently, all right, because they're generalizing. A specific problem, on the other hand, might have the axes labeled unique to whatever the circumstances are. So if you're talking about business math, all right, this would be, $sign instead of Y, right? Or, cost or price or something, right? And X would be, some units sold or something like that. Whatever, you could adapt it to any situation as long as it is exclusively talking about two variables, that variable and this variable, right? I know that these are letters as well, but they have the weird labeling that they do, M and B, because they have unique jobs, right? The things that are attached, right? The thing that is attached to the slope and the thing that is sitting off by its lonesome, those are the genuine variables, all right? And again, you could adapt them to any problem. You can change the labels to whatever you want, right? So there's a word for that, right? So let me just emphasize something here. If this is the model, not to belabor the point, we're going to change it, but we're going to consistently refer to its parts, right? Whatever the problem. Y is what they would generally refer to as the dependent variable of the two. Right? It depends on X and other conditions that are on next to X. Right? Namely, what is the factor here, the coefficient, what is the starting point here, right? It depends on the outcome of these things being blended together. It is set unto itself alone on one side, but it is the dependent of the two variables, the two actual points of interest, right? The X, on the other hand, right, is the independent variable, at least in this arrangement. Independent. I have a hard time spelling this because it's so many EN somethings. Independent variable. Right? Right? It does not depend upon Y. It affects Y. Y. And it can be anything. In theory. Right? At least if it is arranged as such. If you purposely rearrange the parts to be solved for X, meaning X would be alone on one side, then their jobs would change. X at that point would be dependent and Y would be independent. But this is usually the case. Y alone, X not alone. Right? Now, the features that in math world we call the slope and the y-intercept, they have really a job that would be better to refer to as, all right? The M, yes, it's a slope, but to distinguish it from anything else, it's still a slope in a generalization in math world, but in real life, it's a rate, all right? If you, at any point, see the word per, an, or in the context of the problem. An, in, or per especially. Per. All right. Per. Look for that. Then this is the rate. Right? And it has a job. Its job is basically convert one unit into another. On street signs in the United States, at least, we still use the imperial system here, right? We should use the metric system, but we still use the imperial system. Anyhow, miles, right? The street sign says 55 mph, as in 55 miles per hour, right? What is it doing? That rate converts a distance that is a physical linear distance into an amount of time. Right? It converts one unit into another unit. All rates do that. All right? In the context of a problem that is about money in some business, for example, it will convert a number of articles sold into an amount of money. Think of money as a unit. Usually it isn't. All right? It's not measured anyhow. All right? In the context of a problem, the B value, otherwise known as the y-intercept, it is still a y-intercept, a vertical intercept, if you will. All right? But it, again, has a job that you're going to need to look for. Right? The job of this, I'm just going to write it in blue for lack of a color, is basically the starting point. Think of it as, in its most practical sense, a starting point, right? Whatever number it is, whatever the context of the problem, if you figure out that, well, this thing is standing in place of the y-intercept, or what is normally the y-intercept, it is where you're starting in your graph. How come? Because remember, in the real world, instead of math world, there is no quadrant 2, right? There's no quadrant 3, there's no quadrant 4. Everything is just exclusively quadrant 1. So your starting point is relevant, even more than it normally would be. The y-intercept. All right? So you're going to look for, when you read word problems, you're going to look for the word per, and understand that this is really the slope in math world. But its job here is to convert from one unit to another. And if you get something that you identify as being a y-intercept under normal circumstances in math world, in the unique problem, it's going to be where you start in terms of drawing your line, right? Okay. This again would be the independent axis, if you want to go with that labeling instead. And this would be your dependent axis instead of y. All right, now, again, the last thing I want to do is at least walk you through a weird sort of word problem. Right? It's weird only because the numbers are very large compared to what we deal with in math world. In math world, especially early on, we deal with small numbers, right, to get the concept across. Right? When you have a real world application, the numbers may be of a magnitude that is much larger. Anyway, don't be intimidated. It's just the same thing using different labels. All right? Let's take a look at this. All right? And I'll project it here. Alright, dopey, gotta wake up again. Okay. Here's the example that I want to walk you through. I may have to sort of toggle a lot. Alright, there's 3 parts to this, and I feel like when I go through the explanation I jump the gun a little bit, so I'm going to try not to do that. Alright, I purposely wrote this in different colors because I want you to sort of, in your mind, get in the habit of organizing information that way. It doesn't have to be in the colors that I chose, but it is meant to say, this is different than this other thing somehow, right? Or to emphasize. Alright, so Javier owns a business that sells bicycles. Right? He believes that the profit, or the loss potentially, right, from bicycles sold can be estimated by the formula given here. Red alert, all right? Remember, we haven't gone into anything more complicated, so the worst that this example could be is just a disguised version of the model that we have. So immediately above this, I'm going to write the model that we have or that we're familiar with, all right? Notice that there is a letter, sad, lonely letter, on one side of this equals. Right? And then I'm going to write the model above it. Right? And you could form an analogy immediately. Anyhow, to complete this thought, Javier thinks that he believes that the profit from bicycles sold can be estimated by the formula P equals 60s minus 90,000. Again, the magnitude of the numbers is just larger. Right? Where S is the number of bicycles sold and P is profit dollars, presumably. All right. Anyhow, what does this mean? It means that essentially the unique context of this problem, unique conditions of this problem are changing the labels from y to p, all right, and from x to s, all right, but the junk that is sitting around them, all right, still has the jobs that are familiar to us. For example, there's a coefficient attached to the, apparently s is the independent variable, which is normally x, and p is the dependent variable, which is normally y. All right. How would I know that this is dependent, the p, and how would I know that this s is independent? Because of the arrangement. If something is arranged so that this letter is all alone on one side, it has to be the dependent variable. All right, because it's alone, all right, on one side. That makes this have to be the independent variable. Anyhow, the slope is 60, right? And the y-intercept is, in this case, an enormous number, but it is negative 90,000, right? As you know by this point. This is the coordinate, the actual coordinate. It is enormous, right? But this is the y-intercept, right? So therefore it is an ordered pair, x comma y. Normally it's the y value that you see here, right? So therefore, if we were going to even superficially start plotting, and I know I'm jumping the gun a little bit, you could pluck this information out without even reading the instructions, is really what I'm getting at. This is the ordered pair 0, negative 90,000. Awful as that is. Because that is the thing that doesn't have a letter attached to it. It's just a number. All right. This thing, on the other hand, is your slope. Right? Now, you could kind of tell, again, it takes a little bit of experience, and it's really the experience that makes a person a little bit gutsy, nervy enough to go, I know what this is. All right? Which is why you should try to do this a lot, right? Because then you build up confidence like that. And you're correct, you're not just swaggering. All right? If the thing spits out profit, money, and it is, S is a number of bikes sold, then what the slope here, the 60 specifically, is doing without it explicitly being written, this M here is translating a certain amount of money into a certain amount of bikes. All right? Bikes is a weird sort of unit, and dollars is really not technically a unit because it's not measured, but it's kind of filling that job. So I'm reluctantly going to put the dollar sign after the fact. All right? Anyhow, this 60 would be a number above the line. And this, because we want to make it a whole number, a fraction, would make this one bike. Appropriately, the dollar sign should be in the front. All right? $60 converts to one bike. Okay? So if you multiply by a certain number of bikes, there's going to be a cancellation effect of bikes, and it's going to spit out money. That's its job. All right? Now, again, I jumped the gun, but let me scroll down here. All right? I jumped the gun because I want you to see that you can feel it, all right, even before they tell you, all right, what to do. I'm going to erase this gobbledygook for a moment now. Right. Part A to this problem is to try to graph P equals 60S minus 90,000 in the situation where S is smaller than or equal to 5,000. Basically what this is saying, without using the words, is that this is the maximum along the x-axis. All right? You would try to figure out what this looks like graphed. Right? And in terms of the increments that run along the x-axis, don't go past 5,000. You exactly add it or less. Right? That's all that that's implying. do this by hand. It doesn't have to be perfect. Try experimenting with large increments. Now, normally what happens, and I'm here to encourage you, a person with not enough experience will go, how am I going to do that? These numbers are very large, and it's not even labeled to begin with. You have to be not afraid to step in it. Don't be afraid to experiment. You may end up drawing a picture more than once, but so what? All right? When you make a mistake, you are narrowing down the possibilities. You're making progress. All right? So here's what I'm going to do. All right? I'm going to attempt to walk you through this, and I'm going to give you some pointers. All right? I'm going to have to move this for a moment, unfortunately, and I'm going to pull up the graph paper. I'm going to write the information here. This is a reference because we're not going to use this side anyway. Now, for part A, just a couple of things, pointers, if you will. If you have something, large magnitude figures, all right, for part A, all right, the increments can be whatever you want. Take comfort in knowing that. All right, they can be different and also different on the two axes. All right, just be consistent. All right, what do I mean by that? I mean that once you have established what the increment is, don't make them inconsistently a different width as you're going along the axis. All right? What can be different is that the increments that you have here can be different from the increments that you have running vertically. All right? The increments can be whatever you want, which means that even though the grid lines exist as 1 block, 2 blocks, 3 blocks, they're all increments of 1. You can do them a little bit larger. And having done this problem myself, at least 2 or 3 times, I decided that it would be convenient to, focus my attention to just these 2 axes for a moment. From here to here. I may seem like I'm double talking, I hope not, all right? But you'll see that this makes sense in a moment. All right, we're going to pay attention, at least initially, to quadrant 1 and quadrant 4. All right, eventually we're going to get out of quadrant 4 because it's not going to be necessary. All right. All right. The increments that I felt were useful along the horizontal axis from here to here. I'm going to erase this just because it will be messy if I don't. You don't have to erase anything. Is that I'm going to put them in blocks of 2. Right? This is only decided by experimentation. Right? I'm doing it once now in front of you recorded, but it took me a couple of tries. All right? I'm going to make an increment here, 2 blocks wide, and then be consistent and just increment every 2 blocks like so. And then I'm going to decide what the actual number is here, 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 and here. If we have decided, right, that the horizontal, that is the independent axis, which is normally x, right, is instead an amount of bikes, right, and the bikes is, weirdly represented by the letter S instead, right, then this is the S axis, as opposed to the X axis. So I'm going to call it the S axis, right. Remember the conditions that were described a moment ago. I'm going to put this back and just show you the other thing, what I was trying to emphasize before. All right? Graph this, I'm sorry for the mess, when the S value, that is the horizontal, is less than or exactly equal to 5,000 bicycles, which means that we're not going to go beyond the scope horizontally of 5,000. It's a very concise way of talking, granted, all right? And you may lack confidence, but, all right, believe me, you get confidence only by doing something a lot, right? And that includes me. How did I move this? All right, well, this moved for whatever reason. So, oh, I know why, because I didn't, yeah. Right. My increments, I have decided, are every 2 blocks, just because it fits that much in here, all right? Let us call the increment this way, that is 2 blocks wide, 1,000 bicycles. And you'll see why in a little bit. Right? I chose that, again, only through experimentation. That means that the next increment, another 2 blocks, would be 2,000 bicycles, right? And then the next increment, another 2 blocks, would be 3,000. And then another 2 would be 4. And then another 2 would be 5, right? Again, the conditions of the problem are they only wanted you to go up to this point in terms of S number of bicycles, right? So that's the way I've chosen to increment it consistently, 2 blocks wide, 2 blocks wide, 2 blocks wide. But look at the magnitude of the numbers and go, okay, that's fine, you know, don't get mad. Right? Then there's the increments that run this way. Again, they don't have to be the same. It would distort the picture, granted, but even if you made a calculator do that, that's exactly what it does. It distorts the picture, all right? Because if you had it exactly 1-to-1, it would be beyond the scope of the calculator screen, or beyond the scope of the paper that you're writing on. You can't get mad at that, right? Anyhow, the increments that run this way, I decided only from experimentation that, all right, to make it fit on this piece of graph paper, that I'm going to increment these, again, still 2, right? 2, 2, 2, 2, and then down, because I'm going to need 2 as well in this case. 2, 2, 2, 2, 2. The increments are going to be $30,000, because again, we're talking about money, and that just coincidentally happens to be the conditions of the problem. So, 1 increment up is 30,000. I'm going to put this in blue just because it might make it a little bit easier to see it. Maybe I'll use the abbreviation 30K, right? K is in kilo, and kilo is in a magnitude of times 1,000, right? Just to make it fit, right? This is 0, right? Just as it would be 0 for the red. And then down would be negative 30K. Down another 2 increments will be negative 60K. Down another 30 would be negative 90K, right? And you will see why I chose this incrementation this way. 2 blocks, 2 blocks, 2 blocks, just to make it fit on the scale of the paper. And why I chose these numbers. Again, you only can do this with experimentation. I can't really stress that point enough. And I don't want you to be dissuaded because you go, wow, the big numbers, Don't get scared, all right? You may end up having to do something several times in order to get the scale just to be appropriate. I'm going to close my door just because there's a little bit too much light coming in. Okay. Now before I erase this writing here, I want to emphasize or reiterate these points. The increments can be whatever you want. I chose 2 blocks to make an increment. I could have chose 1, but it would have been a little bit harder to see. All right? And also different on the 2 axes. 2 blocks this way means 1,000, right? 1,000, 1,000, 1,000, 1,000, 1,000, right? However, 2 blocks this way, up or down, is 30,000, right? It's a different increment, really. It's a different unit, right? Right? Just be consistent as you're going vertically. Be consistently 2 blocks and then count by 30,000s, or count by 2 blocks and count just by 1,000 this way. That's what I'm getting at. Right? The 2 axes can be different from one another, but try to be consistent. If you just made this a little bit wider randomly, then the whole thing, the whole house of cards is going to collapse. Right? You got to have some consistency somewhere. Right? Anyhow, we're doing part A. And I'm going to continue with my labeling in a moment. Our focus, again, is really just on this side of the paper, what would be technically quadrant 1 and quadrant 4. The rest of the problem, which, again, just not to move the slide, I'm going to show you the cutout here, the printout. I sort of jumped the gun, as I mentioned. What is sitting in the place of the y-intercept is negative 90,000, right? So therefore, if that is the starting point of our graphing under ordinary circumstances, I am going to, now that I took the time to label this, I'm going to put a dot at the location that is the y-intercept, right? The starting point. Right? Is the model again. Y equals mx plus b. This is the slope. This is a y-intercept, weirdly labeled, yes. And in the unique problem, the labels have been changed to be p instead, and the slope is 60 over 1 technically, and s instead of x, and negative 90,000 instead of b. Anyhow, the good habit we have is we take the y-intercept and we start from there. Right? This is the starting point. So, in old school math world math, it would be 0, negative 90,000. So on my graph, which again, I only decided this labeling by a lot of experimentation, would have me put a dot right here, down here. Again, I know I said before that, hey, you're just working with quadrant 1. All right, that's true, but we still need to place the start. All right, so I'm going to work down here, and maybe I'll erase some of the line, all right, so that it's just up here rather than down here as well. All right, anyhow, that's the starting point. Negative 90,000. I'm just abbreviating it, negative 90K. All right. Now, if they ask us in part A, graph this equation, P equals 60s minus 90,000, for the situation where this is basically the maximum, where S is no more than 5,000. Right? Let's see what we would get. Right? We have we have our starting point, and now we would need to use our slope. Now, because the increments are so tiny, I'm going to cheat a little bit. I'm not going to go with using the slope so much as I'm going to use the y-intercept, the x and y-intercept. That is a y-intercept. If I really want to graph this, I'm going to go looking for the x-intercept because I know that I have that as an option. And it would be easier in this particular problem because of the magnitude of the figures involved. So, here's my calculation. Oh boy. Let's look for the x-intercept because we need a second point. What is the coordinates of an x-intercept? It's x, whatever it is, and then 0 for y. So if I stick a 0 in here where the p would be, because p is representative of y in this particular problem, I can now solve this. 0 equals 60s minus 90,000. Specifically for the s value, that would give us a dot somewhere along here. I just have to do a little rearranging algebraically. I'm going to subtract 90,000 from this side. Opposite of subtracting 90,000 would be adding, really, 90,000 here. There's a cancellation effect. And then what have you done on this side, you do on the opposite side. That makes it legal. 90,000 would be over here. All right. So 0 plus 90,000 is just what? 90,000. And over here, there's still this 60 with an s attached to it. How do I solve for s? If they're pressed together, what operation is in between them? Multiplication. If I want to justify moving 60 from here over equals, I have to divide by 60. There's a cancellation effect, and if I did it here, I did it here. You could use your calculator, but the bottom line is that if you have 90,000 divided by 60, right, that you could pull some tricks, right? Namely the zeros. A pair of zeros would have the same relationship if you simplified as such. That's like dividing by 10 without really consciously thinking about it. There's a legal reason for it. Then you would divide 6 into 90,000. 6 goes into 9 roughly one time. The difference between 9 and 6 is how much? 3, right? So I'm going to squeak a little 3 in here for short division. And then it's 6 into 30. Exactly 5 times, right? Which is, there'd be some cancellation, and you get a 0, and then it would be 0, and then 0 again. That's a weird blue light. And this is the figure, right? 1500. The x-intercept, there would be a dot in theory. Again, I'm cheating a little bit. I'm using an alternative method than to use slope purely. Just because if I did the slope, it would take me a while to get up. And it would be, the increments are so different, it would be hard to see. I'm going to put a dot at this location, at 1500, comma 0. This is why ultimately I chose the increments that I did. Because if this first increment is 1,000, and the second increment 2 blocks later is 2,000, what would be exactly in between them? That number, right? That's why I chose the numbers that I did and the increments that I did. It would be easier for me to see, all right? Anyhow, I have a y-intercept that was given to me, and I calculated an x-intercept. And since I'm dealing with a line, all right, that's all I need. Now I could draw. So I'm going to whip out the ruler here again. And as carefully as I can, this is graph paper, of course, on purpose, I'm going to connect the dots. Like the placemat at the diner, right? And I'm going to overextend the line so that I don't have to do calculations anymore. The purpose of drawing the picture is, as they say, the old adage, right? A picture is worth 1,000 words. If you overextend the line, i.e. if you extrapolate the line, you can predict what the other points will be beyond where you actually calculated. Anyhow, and you do have to, especially doing this by hand, you got to be very careful with the line. Use a pencil point, not a marker per se. I'm just stuck using what I got. All right, anyhow, this is the answer more or less to part A. It said, graph this. All right, it didn't say how to do it. It just simply said, graph that equation up to and including 5,000, right? All right. And then I just wrote this note to say, you know, you might get a little messy, all right? So again, don't feel bad if the first time you do it, it looks a little sloppy, right? If you're generally running from what appears to be the third quadrant up to the first, and you're definitely going through that point, and you're definitely going through that point, then you've done everything right, however sloppy it looks, all right? Anyhow, everything is copacetic. Let me erase the unnecessary information now. And continue. Part A was to graph, and part B, you will see, is to calculate. All right? This is P axis, and it's what would be dollars. So green seems like an appropriate color when we're talking about the vertical axis, because it's money, right? The lean green. All right? Anyhow, let me read this to you again, just not to move the slide back. Right. B, from the graph, right? Estimate the number of bicycles that must be sold for the business to break even. This is a very vague way of talking about how the calculation would work out. We actually already figured it out. Right? Again, I jumped the gun a little bit. Right? What does it mean to break even? break even as a subject with a definition is going to occur, I think, in section 6-7, so it's actually premature to bring it up here. But it was, nonetheless. I stole this from your textbook. All right? Break even implies certain conditions. All right? So without the formal definition, to break even means, all right, neither profit nor lose, nor loss, right? Symbolically, if you are neither here nor there, neither up nor down, nor right nor left, what number would you use to symbolize that concept? 0, right? Well, if this is the formula, P equals 60S minus 90,000, right? We already did the calculation, actually. The profit that is neither up nor down, that is neither positive nor negative, would be 0. It would be the x-intercept anyhow. And we just calculated that in order to draw the picture. Again, I guess the original conditions of the problem would be like, hey, use the slope to graph this. But to me, that wouldn't have been easy because of the increments that I chose, right? Right? If I would have used the slope to graph, it would have been correct, but it would have taken me a while, because of the smallness, the acuteness of these spaces and how large these increments are compared to one another, negative 30,000, all right, to graph it, right? I would have to go from here up 60, over 1, up 60 over 1, up 60 over 1. But that is a magnitude that is so minuscule it would be impossible for me to see. All right? So I went with what my intuition would be. Use a different method. Use 0 anyhow. Dumb luck. All right? So we already did the calculation. What did S end up being as a result of putting 0 here? 1,500 bikes. All right? That's the answer to B. This is B. That point there. So that's why this is really relevant, right? If a business doesn't want to fall out of existence, you got to get above the axis here. If you're selling something, you could be selling 1,000 bikes and still be losing money below this line. If you just meet 1,500 bikes, then you're not going to go out of business, right? You'd have to get beyond it, though, to make a genuine profit. Right. One more of these. Right. From the graph, right, estimate the number of bicycles sold if the profit from selling bicycles is about $150,000. Right? Now, notice this figure is incremented, it's a unit of money, basically. That means that, let's pay attention to the vertical axis for a moment. If the increment we have decided, me primarily, is 30,000, fine. Let's see how far we can go up the axis here. All right, I'm going to just be consistently in twos here. All right. That's 30,000. Another 2 blocks would be 60K. Another 2 blocks would be 90K in the positive direction as opposed to the negative direction down here. And then that would be, the next one is 1,200, it'd be 12, so 120K, 120K, $120,000, all right, this is money. And then another 2 blocks up would be 15, right, so 150 technically, all right, which is what the question is really asking for. We can do the calculation because we have the equation P equals 60S minus 90,000. And we could validate a suspicion we may have. But if I drew the picture extra carefully, and I tried, all right, then I might as well just utilize the picture to tell me the information that I'm looking for. What it's asking is, how many bikes would equal $150,000. Right? That's what the question is essentially saying. How many bikes do you have to sell in order to profit $150,000? Well, here's $150,000. Let's scoot this our attention over to where the line actually exists, which would be here, and then connect it with where it would exist on the horizontal axis, which would be what number? At $150,000, this line predicts that the number of bikes sold would be 4,000, right? Without doing a calculation. So what I'm going to do is just to verify. Well, if I put 150 in here, and I'll erase this side of the board just not to get in the way. If this is the formula, P equals 60S minus 90,000, and I substitute the figure of 150K, so 150,000, in place of P naturally, because it's profit, so money. Let's see the way the math would work out to verify. All right. I would naturally play the game of algebra to simplify, right? To solve it. I'm going to move 90,000 from where it is over to the opposite side of equals via opposite operations. I accomplish that by adding 90,000 to both sides. So this cancels here, and then I would add 90,000 to 150,000. The magnitude of the numbers is uncomfortable, granted, but this is still the same logic, so we could take comfort in that at least. 0, 0, 0, 0, 0, 0, and another 0, 0, comma. 5 and 9 is 14. Carry that is 24,000. 240,000 is the magnitude. Right. Over here we have 60s. Right. If we now divide by 60, cancels here. This will tell us S's number of bikes, weirdly, right, instead of B, all right, and then we divide by a 60 here, all right. Again, you could pull a trick if you're doing this by hand of crossing out a pair of zeros above and below. It's like dividing by 10 without really thinking about it. Anyhow, the relationship is the same. If you divide 6 into 24,000 now, right, we'll see what we get, all right. 6 goes into 24 exactly 4 times, which is 24, and you get 0. And then it would be 0, 0, 0 up to there, which is what the graph predicts, what 4,000 bikes. As is said, this is often the case in math. There's more than one way to go about a problem. One is not better than the other, but it's good to have options, right? And in the long run, you could be more strategic. As long as you realize that you have options, you could decide to do something this way or that way. That's what I did, all right? I chose to use the x-intercept right off the bat, all right? Anyhow, you can't get bogged down with little things, right? You have to kind of etch-a-sketch your brain and go, all right, I'm going to just not think about that for a moment, you know, like the scales being not, you know, being so huge, right? Or the scales not being 1 to 1. They're not 1 to 1. This is 1,000, that's 30,000, all right? It's 1 to 3, all right? Or 1 to 30, rather. Anyhow, that's that. 4,000 bikes. All right, that's this. All right, anyhow, thank you for sticking with me for nearly 3 hours. This is section 6.6, all right, for people in MAT-114 specifically. Anyone else is watching, you're welcome, all right, too, all right, but you're not responsible for this, all right. Anyhow, I will shoot the 6-7 video on our appropriate day, which is Wednesday, of course, all right. See you soon, all right, be careful.